Good evening. It's Tuesday afternoon, June 20th, 2023. And today I imagine I'd talk some more about differential equations, or rather really just part of the mathematics overall in the synthesis and the analysis and the study of the science that is mathematics, the practice that is mathematics, from what I can understand of it, from what value I've derived from trying to learn about it, and how much trust you can have in something that is essentially where there are right and wrong answers, and it can be derived to any given person's satisfaction, very much so why something is or is not so in the realm of the purely mathematical. So this is something that has always interested me since a boyhood, to wonder how I could go about knowing how the laws of the universe worked, and what things would be necessary to bring with me in the tiny little travel kit that is nothing but the contents of the brain that could possibly bear up in being able to solve anything or understand anything, or to make it so that there be a descriptive notation to really tell its story. And if there's something I guess I garnered some experience from, and some I'm not sure how you'd say it, some value from, was when I was a child, and I had a paper route. And so I was 12 or so years old, and the first job you could get that was out of the house, that wasn't farm work or something like that, was the paper route. And so I was proud of myself for getting up every morning, like 5 in the morning, and I would go collect a stack of papers from the corner where it was dropped off, and I would wrap up each of these papers in these little rubber bands I had to supply, and then put them together in my kit, my bag, the front and the back. The letter carriers, the paper carrier's bag, and either walking or getting on my bicycle, then I would slough off down the half a mile or so to the neighborhood where my route was, and I would go from the house to the house, and I'd been acclimated to know which houses had subscriptions and which didn't, and it changed every now and then. And some people really became adamant. It's like it's got to be on the porch, vis-a-vis, anywhere in the front yard is good or something like that. And then when it rained or snowed, it was necessary to be even more careful, and make sure everything was put away. Or I had to buy all these bags and put the papers and the rubber bands in the bags and deliver each one of those so that they would get their morning news. So what I had as a habit was I had learned about decimal and binary and powers of 2. And so then what my practice was as I was walking along, keeping cadence or what, I would just count up in powers of 2. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. 4,096, 8,192, 16,384, and up to 35,536 or so. Running out at about 2 to the 8th or 2 to the 10th. And then it's kind of apropos that then it kind of starts again in terms of kilobytes and kilobytes and these kind of measures of things. In terms of kilo being thousands and kibi being 1,024s, and then the powers in the units called the kibibytes, or the kibi units vis-a-vis the kilo units are 1,024, and then powers of 2 vis-a-vis 10 to the third or 1,000. So this I felt served me well later, because I had it already acumen, kind of like studying the times tables, knowing all the times tables, or knowing the modular differences and numbers between them and the next higher multiple of a power of 10. So to be able to add 2 numbers by their tens parts, and then subtract what was left over, and to end up with ready sums and this kind of stuff. These were little lessons I figured out for myself, and everybody should, in terms of after everybody does the times tables, everybody is able to perform long division and that kind of thing. And they didn't take some students up to like 6th grade or so, and that was basically graduation from primary school, was knowing the times tables. And so I was very lucky in that manner, and then I had a lot of enrichment in school, and access to computers. That's where my paper route money went. It wasn't enough to actually get anything from my computer, but it was considered a reasonable down payment for me to put down my own money and then to go towards it and that kind of thing. Oh, and it kept me in tire patches. I didn't have many flat tires or anything like that, but I always had a patch kit and could patch my own tires, my bicycle, and all this kind of stuff. That didn't last very long at this job, but it lasted for quite a while, and became proficient at it, and I really kind of gave it up because I didn't really feel it was worth the money, because of course it wasn't much money and at all, but it was a job, and so I was happy about that. Then later I got computer work, and so I had one of the cushy computer programming jobs in high school, and then later carried that out into, in a career work that I know everything about computers that I feel like I really need to know, and it's just a matter of practice and effort to put that down on paper and get figured out how to make that so that it's codified, formalized, programmed to understand large programs and regions of code that range into the tens and thousands and millions of lines, and also into the tens and hundreds and thousands of person years of labor and effort that went into building the systems and understanding these kinds of things. So besides a facility with mathematics, and the only other key thing that kept me from being a complete illiterate anumeric person with otherwise a brain, and nothing obviously wrong with them, not missing any fingers or toes, nothing obviously wrong with them, no reason why they can't make do, it should be independent. At any rate, was reading. If that's the other thing I did, is that every day pretty much or so I would have my bicycle, and I even got it so I had a little basket on the front of the bicycle, and I would trundle it downtown into the city, this little town, and go to the little library, and I would go through all the shelves, and I pretty much picked out what looked interesting and what looked boring. It's like, no, I don't want to read Frontier Tales. I'm more interested in the Black Cauldron. Or here, yeah, let me read these 30 books you have in the series of Oz, all the Oz books. These are something particularly critical, I felt, to having an understanding and learning enough of the language and the literary. Even though they're silly, I knew they're fantasies, and that all these novels were in some sense fiction, and the Planet of Tears or something like that, and all kinds of Tom Swift. If you ever heard Tom Swift, there's about 100 books about it, and all kinds of these things that this little library had, and I read a bunch of shelves, and I had the longest list on my library card by far of any youth in that city, in that town. It's a good, nice little town. So anyways, to just kind of extract from that, it's a long ways to the top, a long ways to understanding enough about mathematics to become both that it becomes easy and that it becomes internalized, the internalization. Now, what does the internalization mean? The internalization basically means that the concepts, once learned, are synthetic and integrated and become available in their access to not just memory, but to overall cognition. It's not necessary to recall every little formula you ever learned, and in fact, it's an exercise in what you have to forget, or the limits of the mind, and as to why the abstraction of mathematics makes it possible to arrive at something where the methods, the analysis, can be redone on demand. That's that kind of skill of being able to think on one's feet, or to land on one's feet, or gently, and the ability to reconstruct theorems vis-a-vis the rote in the memory, R-O-T-E, rote, and regurgitation, they call it sometimes, which is the regurgitation of facts that have been provided as upon the stimulus, the response to the fact. The critical part and the thinking part is definitely combined in both the acculturation of literacy and the enjoyment and reading for enjoyment and facility, and also then the number sense. Here there was a lot of talk earlier in the considerations about the basic theory or the basic philosophy, why there's something rather than nothing, that the number sense after the object sense is all that's available to reason. That's never found diagrammed in a book. It doesn't matter that somewhere in the Nazca lines in Peru that they drew pictures so big they could only be seen from space, or there's some kind of example that I read about in like Chariots from the Gods or something like that, with regards to the ability to comprehend infinity or other concepts not standard, or the continuum itself, a continuum of real numbers and the properties of numbers, plainly, is an entire exercise that is only matter-of-factly, abstractly. That does not by any means make them less perfect, complete, whole, and real. They're indeed, and in all matters of fact, more so. It's much more so. Why you call it the ubiquitous success of mathematics in all matters of philosophy for the qualitative and quantitative really holds so, and is as much part of what is necessary to get higher order function in all kinds of fields, and the ability to approach any and all kinds of fields in the continuum mechanics and the dynamics and the analysis with anything more than the facile. It is anything but shallow. And while at the same time, it's one need not make it so committal. The ontological commitment to a theory is that which basically takes the weight that it has, the inertia, the momentum in the cognition and the theory of how it holds so, like a ground truth or the fundamentals, the inviolables. What are the laws of the principles? This ontological commitment, then, when it comes to theories of real things in reality, really depends on what the things are and why they relate to other aspects of objects in theory. The strength of the mathematical objects is that they give their all. They are ontologically committed within themselves. The mathematical objects, logical objects, mathematical objects are here the same. Sort of geometry, and as has been discussed here, the objects of arithmetic and algebra and number theory and geometry and function theory and topology, vis-a-vis the foundations and set theory and type theory and category and the or part theory, and otherwise matters of relation very low in a theory of a monotone or monotype universe in the I hesitate to say univalent, but in the theory of the truth and the univalent, with the illative and these kinds of things as fundamental concepts, that the ontological commitment to mathematics is successful, then is right next to the ontological commitment to science and statistics is successful. They essentially guarantee themselves once you get to know them. And so sometimes that's bad because the numbers are against me. The numbers are always against you. Don't worry about it. That's where your other ontological commitment to other things will see why your overall work will entail that your wishes come true. This is a kind of thing to help relate people who don't necessarily like mathematics, that it's not mathematics' fault, and it's not out to get you or anything like that. And in fact, it's the best kind of friend who really doesn't care at all, except that you believe in the same truth as mathematics, So as far as that goes, I've always found it interesting. And then I wanted to study foundations and understand what society, what was found authoritative as the entire study of mathematics, because I knew very well that it couldn't be like, although it is in some senses, and sometimes it's matters of definition, what is considered mathematics or not considered mathematics. I've been reading this interesting book called Equations from God by Daniel Cohen, and it's about whether in 1850s Victorian England, in the time of De Morgan, and when logic became, after Boole kind of stood up as after the Enlightenment and in the era and days when the argument about authority was that mathematics was true and pure, that it's its own ethos, and so in that sense it by no means contradicts other monisms or the monism a theory of mind, in a body of thought, in a world that's a middling world, or the world, in a universe, that all the concepts that go along with monism and monotheism kind of hold together very, very, very much better and well when what would have been some perfect truth of logic and mathematics is a holistic, if dually self-inconsistent thing to be consistent, as it is. So in this manner, then after studying foundations and philosophy for all these many years, I really felt and found that I had as much more of a grasp than I ever would have wondered to have, and that it becomes then that all the different applications in the fields don't entail ontological commitment beyond their immediate definition, and the applications, when there's models of physical models for mathematical models, or the qualitative is fair and accepted as mathematical, or but besides also is just plain qualitative, and the qualia. That then, and knowing enough about statistics and probabilities, then I feel like the numbers can't be against me, at least if I can read them, and they're going to be all right. So those are the kinds of things that get into then why, in trying to study this second course, differential analysis. The second course has been discussed. That for the first course is instruction, internalization, application, and also the relevance found in all the other fields that use for their applied methods in differential analysis, and whether, for example, that's time series terms in the asymptotics and the asymptotic analysis, or as well, for example, something like the not that so much the concrete mathematics, as we call that, the concrete and the finite combinatorics, but also the application dynamical models more generally, that it has become then relevant to know what and how these things are, to help figure out what goes on in terms of the how you might say application and the availability of application of these things variously. So, looking into reading some more of these things. Here's this function as complex variable where we left off. And it's written by this Phillips out of Cambridge or what. Let's copy this book. It's from Dugway, Utah. And I'll go look to see if I can find the dog mark or the ear mark. There's not one. And so this book's been gone over a little bit. It has many pages that have been dog-eared or folded on the corner to make an ad hoc bookmark. This is preferred to ripping off a corner or otherwise something that makes a permanent change of the book. Writing in the book is acceptable, but I avoid it myself. And then there's also otherwise usually the application of the slipcover as the bookmark. So we talked about the Jordan curve theorem and a point at infinity. Complex numbers, complex planes, differentiability. There is discussed continuity. The function is continuous. So in mathematics today, the notions of the definition of what is a continuous mapping is a continuous function. And so for that, then the continuous function is the usual definition in continuity because it's lacking a definition of a continuous domain. The continuous domain is more of along the lines of that there's the line rails, the field rails, or the signal rails. And this is otherwise left out because in the standard curriculum today, they only have one continuous domain, the line rails. And as a prototype of a domain, then it's according to particular choices about the axioms of least upper bound, measure 1.0, and the open topology. There are other ones with regards to then that the besides the those applications after the field continuity, there are the line continuity and signal continuity, other continuous domains. And so otherwise, a continuous function would still be so and hold and maintain its properties in terms of, for example, a domain that's like the Dirichlet function, only defined on the rationals, which is not continuous. There are rational numbers in the real numbers, so the rational numbers are not continuous. And something like the intermediate value theorem would only seem to hold so about these continuous quantities. So and that's put in as for delta epsilon x combined with least upper bound property, and then later with measure 1.0 being another axiom for the completeness, the Dedekind completeness of the complete ordered field, that otherwise this line continuity has its length assignment to make measure, and it has completeness trivially, and dot dot dot. And the signal continuity basically reflects that it has analytical character according to the sampling reconstruction, or the space of the functions that live on it, that function theory, as was mentioned, was probably the most varied set of definitions over time, because when mathematics changes, they just change the definition of function. That otherwise meant most of the other aspects are kind of set in their own domains as without being adjusted. Here, of course, as well, there is discussion even in arithmetic separating addition and division, making them two different worlds of things that happen to live together, and it's just a relevant fact that then when they're put together, they do make the numbers, that otherwise they make sums and quotients. This is not unfamiliar necessarily to people who study algebra and abstract algebra, and the algebras or magmas, anything that's defined by operations and isn't quite an algebra, or something along the lines of parts of an algebra, like a group or a ring or a field, called magmas or algebras. That for people's arithmetic, then there's the notions that the rules of arithmetic and the laws of arithmetic make so for those objects of the numbers, which are number theories mostly. Call arithmetic number theories, and number theory arithmetics pretty much. That the objects, when they're elementary and primary, are from that subfield and that part of it. Then there's that the algebra is at once very flexible and fungible in terms of the quantities, but it treats quantities that otherwise are not elementary. This has been discussed in terms of the derivations and what happens between different formulas when there are incidentals or consequents or the implied that need to make it so that the quantities stay together, that otherwise algebra is free in the terms of variables are independent and thus can be treated as of a type, and that equations can be reformulated to solve for variables. And that's one of the most usual courses of solving for things, is to solve for the variable in terms of the other parameters and the forms which express relations that make equations. It's very, very usual. Systems of equations. And so then these differential equations and the differential systems are systems of equations. And also the transformations and the derivations that so follow, that make for the manipulations and the transformations that they are, that those make for related systems of equations. And that then for algebra's place is that when the objects are geometries or number theories and not necessarily algebras, quantities, it is pretty much a non-standard variety to think of something like that, but it's true, or it's evident in how they exist, because the same kinds of relations that one models for the other, that are algebra models for arithmetic's objects and vice versa, fall apart the same way, but they can be put back together different ways. And so when you think about how a course is, and it's like, driving up the ridge, well, what's on either side of the ridge, whether it's actually just driving up the canyon, and if you go off on either side, you'll just kind of just stay right off the road, is one thing. But if it's actually driving up the ridge, and if you go off on either side, you fall off the ridge. These are different things about how they add up and come together, and one way to look at it is division makes it one way and arithmetic makes it another way. Then either way, what it is irrelevant, that when they come together, it's linear and combined. That then this notion of the deconstructive arithmetic, making for the modular, makes all these other things that are elementary themselves. and that have their own bodies of definition and realms of relation. And those are then how to put those together, part of this whole notion of mathematics as objects. Then that they all have to live in a universe of mathematical objects, and they have to be essentially or fundamentally at some point elementary in a particular least related kind of thing, like a set in a set theory, has been the usual approach of modern mathematics to model theory and proof theory, because model theory and proof theory are one and the same. They kind of model each other and prove each other. That they're equi-interpretable. That the interpretation is the relation of objects of two kinds of domains modeling each other, proving each other. That it doesn't take too many types of mathematical objects to really have a handle on pretty much all kinds of mathematical objects, elementarily. Then, though, that all the richness and detail and the higher order and rank and form and their completions, and then also in these extensions, the infinite series that add up back to finite things, that's where a lot of the complexity lives, and a lot of the wonder of it arises from that trying to figure out how to construct smooth forms from angular forms, or geometric objects as from the application of the classical constructions of geometry. Have that those are the kinds of things that get into how to roll it up and to figure out how to implement an analysis, the continuum analysis that involves the real numbers and how they are and this kind of thing. So taking a look around here, then back to this brief page talking about continuous functions. So all that went into the notion of the continuous functions. Why is it let out to just be that as long as the function's difference, if it's small enough in the domain, it's small enough in the range, and the order is maintained, that if an order is in so in a small enough region in the range, that the order is so in a small enough region in the domain, that it's a continuous function? Well, because then it applies all these different terms about proximity and proportion and the affine and projection and perspective that make it hold true that what's so from the one side of the relation is reciprocal and so on the other side of the relation. It can be proved that a function which is continuous in a bounded closed domain is uniformly continuous there. So that gets into notions of convergence, like absolute convergence and uniform convergence, and then uniform continuity, these stronger definitions of continuity. Keeping those straight and arranged and organized by the attributes that define them gets into the problem of keeping attributes with objects and the semantics which apply according to attributes besides elements. That the elements have semantics, then it's whether and how the attributes change those. That exceptions are rules are exceptions, that otherwise they're just a natural sort of flow or tendencies and propensities that implement this restitution and oscillation for this dissipation and attenuation as a complementary property that exists for any given property that explains and fills out the other side of a dialectic that makes it so that something is the same thing as everything that it's not. That's basically a fundamental result in the universals, that if the same thing is taking something like you have one apple, and you take one apple out of the universe, the whole that it leaves is that apple. The context is the complement in the whole universe of things. What it leaves is it. All the roles it fills, all the relations it has, all the places it is it. Now, out of the context, is it still the same apple? In a sense, it is. But you've established where it lives in the context. And then does it become indistinguishable or indiscernible from any other apple in the barrel or bucket? It can be. That's a property where the attributes that define it beyond the elementarily of its being discernible or distinguished isn't necessarily relevant to its identity as an apple, the apple, and that is a kind of a way to look at universals like so, how it can be that there is a universe and things exist in it, and that for all we know, it could just vanish at every instant and come back together in the opposite, as if it was just continuously varying, that it was constantly change that arrives at the same thing, is made understood insofar as that it doesn't contradict itself to be this way, if it is that way, and it can be that way, to just be its own complement in the universe, and then the complement of the entire thing leaves it the same. This gets into the universals and why that is part of philosophy and objects. So that for something like, when you think of an Immanuel Kant, and Immanuel Kant basically he had stuff like the usual thing that was the role and necessary aspect of philosophers and mathematicians in those times to prove the existence and relevance of God. And now this is a given. Can't disprove it, and also it's super scientific. And but then it had to be also explicit and made part of the very vein and frame of things, because it also pointed to all manners of where governments and political bodies claim to derive all their legitimacy. So, anyways, then there was the nous and the phenomenos, and so the phenomenos is the phenomena, the world of phenomena, that which one can sense, available to the senses, available to the sensuous, physical, concrete perceptions. As discussed before, the mathematics is only so available to reason. So this is part of the nous, this nous. So the noumenon is like the phenomenon, but what it is something that's real and a mental construct, or the result of an idea. It's an ideation of a sorts, that it exists. Mathematics and truth, it's a truthful thing. So anyways, one might aver that kind of notion then it gets into what's called the thing in itself. This is one of Kant's ideas, that whereas in the same kind of era that Leibnitz had as monadology, that monism, which is just an extension of the ancient traditions, that there is a whole thing, a holism, a universalism, that there's then this the thing in itself, or the Ding-an-Sich, German words, Ding-an-Sich, thing in itself, has that the idea is that as a fundamental quantity, like an infinity, it's in itself. The universe is in itself. Zero or empty, it's in itself. And so that is a property, it's a property, it's a property. And so at the same time, it's like shouting that that's part of its logical property. It's also the slippery slope and the shifting sands. And these are references of things that go to what would be the intractable and the reductio ad absurdum, or ad infinitum, or ad libitum, or however you might want to care to phrase it in Latin, that they involve what would be beyond the inductive and beyond the impasse of the inductive. Here, that's what's framed the limits of induction. When there exists the deduction, is called the impasse. It's kind of like a bridge, except it's a chasm, and basically the point to induction is if it ran on into it, it would fall off the bridge. And so here the idea that there are these bridges is this kind of thing about the universe in itself, the context of the universe in itself. That in this way, then, when you think of a fundamental object of a logical theory at all, because the idea is that it can't reduce to all theories, like finally we've got a theory with an object of thought in it, and only one. But it would be the Ding-an-Sich. And so he started to ascribe properties to it, and then we call this technical philosophy, because it's philosophy, which is, the love of thinking, love of knowledge, or how to figure out to make for the complex and the sophism to get back into the sorts of the booking of it and this kind of stuff. Then the technical philosophy is in as to where that beyond just when you talk about morals or ethics, for example, other things that Kant and Hegel, who's part of the technical school and canon, got into morals and ethics and roles of individuals and roles of bodies and roles of those who govern, that's not included, although it is a social construct. But the technical philosophy is just for the very objects of reason themselves. So we might look to Descartes back there, and René Descartes has on his philosophies and meditations on discourse on reason. Similarly, the Dzogchen has pointed out from the Buddhist tradition very much has what we call a dialectic in getting into the reason of these things, this technical philosophy, that the objects themselves exist and are things, and even when they're a part of the nous or noumenon, they're noumena or noumenon, they still exist, and then they are fundamental. Then that they would have these kind of properties that reflect infinitely and ultimately and so on into themselves, as for like the Ding-an-Sich or this or that this is so how it is that something like the thing is the complement in the universe of everything that it is not, ends up being like a thing. And then that's not always so in all the models of sufficiently large things. What do I mean by that is arithmetic. And the objects that are sufficient to model and comprise the objects of arithmetic. This is called an arithmetization. You're making an arithmetic of something. You're making it so that it's represented by integers, and then you can figure out either integer relations upon them, and maybe that's all that's necessary to establish how something is why so, or you can build up a whole analysis out of that at real numbers. And so when we look at how this kind of universe of these things has to share is that there's only one universe of the mathematical objects, or there's only one numerical resource that can hold a copy of the arithmetic integer continuum at a time. And so if there's more than one use made of it, there needs to be a structure, a bookkeeping, a scaffolding that makes it so then that otherwise what would be relation in relation wouldn't be erased and lost. Even though that later it can be discarded because it's fundamentally resolved that what's model is a model is a model, and you can make it so that then they're abstractly of a sort and together, and that they're replicas or evanescent, or that the sand cast mold washed away still requires that there's all what's necessary to keep in mind this framing. So this gets into funny ideas. It's like, well, what if we have an infinitude of numbers and they go from 0 to infinity and come back to -1? A great circle, a great wheel, a great circle of these numbers. How is it so that it can be that when we think about the negative numbers, we always think of them as starting at 0 and just happen to be reciprocals and inverses of increment, and addition the other way, subtraction the other way. Vis-a-vis, what does it mean when the numbers just go all the way around and roll over and wrap around back to 0? The infinity is -1 in this underlying model that builds it. Well, that's the thing. It is. It's like that the numbers and integers are modular. that the properties of it being incremental, which are so valid, are only a complement to that the properties and characteristics of it being modular are so relevant, the integral moduli, the multiples, and that those multiples are even again, and those multiples break down in the middles and have their fractions over there, and they roll over. The modulo, is the operation that defines this, clock arithmetic, the odometer, any kind of example making for clock arithmetic or the modular vis-a-vis usual arithmetic. This is just to make it examples of why the technical philosophy, once it arises at a thing and a universe for that thing, that then other things follow from that and build in the middle. And so it's in this sort of way to look at these as fantastical objects, and they can just be kind of whatever sort of thing that they are, in terms of that as fantastical objects, they're abstract, and you can always, and another nice thing, again, back to the lack of necessary ontological commitment to mathematical objects, their relations and their consequences logically that so or don't apply can always be kind of just interpreted as theoretical, and they all live in the theory this way. They all can live in theory in court even by their illogical properties or inconsistent multiplicities properties this way. Is that the this notion of the integer continuum as then a structure that lives in a numerical resources, a continuum of mathematical objects, could very well be modeled as sort of this way. And even as that being kind of a fantastical example, infinity equals -1. It's not so unfamiliar sometimes to even the models of physics and their interpretation of things. Like if the universe was finite but unbounded, that something could go all the way through it and come right back to us in the middle. Does not seem very likely, but the idea is then, and these models get smaller and smaller, for example, and become the cosm, the microcosm of what is this world, this cosmos, the cosmological clockworks, which is this whole total field equation, all the differential systems that come together. That this microcosm starts falling apart, what all it supports. And there's two ways then to handle that. And one way is to just truncate it. This is the usual way too. Just truncate it. It's like we are dealing with bounded quantities. That's simple. And in fact, then we can build our whole theory of like we are only going to start piecewise, bitwise, in truncated, bounded quantities. And as we establish results, as we establish results that come up and through and over and about these things, they're going to continue to be kind of just carried forward in this incremental sense. In this manner, we'll have it easier to have the induction always carries, and we're not dealing with any inductive impasse, because all we'll have to do is just keep this right linear way of thinking, and it's fine. It's a very big strength of the standard, and it's linear, and linear means you can follow it, and linear also means that it goes straight. These are the kinds of things that go into why the standard is the classical. But then the other way, besides this truncation, is the notion that the model basically includes on either side what would be the object that has the relevance for it. For example, if you shrink 0 to infinity to 0 to 100, and you call 100 infinity, or you have to reserve some values on the range for what would be the numbers with these properties. Well, that's not going to help much because once you get past 10 and counting and using any numbers, then all the things that have to do with square roots fall out. But at the same time, until you get past 10, when the maximum number is 100, and you treat things in terms of the maximum like that, like divided by 100 must be 0. That this is as well, and indeed is as much so, the usual application of the modularity and these other properties of the numbers about how they're applied. when the percentile, for example, is something like that can be expressed in terms of both what it fills and what it is a portion. So that's just to make clear that then it's kind of so for all these other properties that end up being for these mathematical objects, when you have to reduce that from the universe to mathematical objects back down to what is in a classical whole, a monist's holistic's hologram of these numerical resources where it lives, that it somehow has these same properties. And so this is kind of when you hear about the Ding-an-Sich, this notion of Kant, for philosophy and technical philosophy, it's not just a set that has a member itself, although that's the usual model of such things, something that relates to itself, compared to that it's a circular definition, that it's regressive itself. These are other usual properties, and here it's been framed in terms of the restitutive and the dissipative. What forms and constitutes something, or what is attenuative and is the vanishing of something. These are, again, complementary duals in these properties. And so, pointing back to that is that the Kant basically establishes that the universal fundamental primary objects and elements of the overall theory of the logical objects and mathematical objects have to be this non-standard way. They have to be this superclassical way. They have to be elements of the noumenon, and also ones that don't have ready models in the phenomenon, which the classical do, and the linear do, and the inductive do, which have any number of ready models by making it so without any loss at all. And they're just like count and change. There's no reason to ever consider that the ontological commitment of mathematics to it or it to mathematics ever changes. But in the objects of the whole mathematical universe, there is that they always do. Now, and then it gets into how that can be tractable. Well, it becomes tractable great, because then you end up assuming, and the idea is to make no axioms, because an axiom is unfounded, it's illegitimate, it's unjustified, and that is only to reflect that in terms of it may still bear fruit as all the truths that so follow from it, but if it's wrong, then it's mistaken, and if it's a false axiom, then at least some of those are false. So the idea is to figure, though, that then there's at least one universe of mathematical objects, and they're all true. And then to be all true, then they even have to have these properties of being these infinitudes, and the Ding-an-Sich, and the noumenon, and that the order type of order types of ordinals is itself, yet it's also larger than any maximum one. The order type of all ordinals would be itself. The universe of mathematical objects contains itself. The empty set is either unique and singular, or there's one for every apple. These are various things, and that again, it was kind of discussed here a while ago. Though, well, what's then the first axiom there is? Well, it's inverse. It's whatever there is, it's opposite. And then from this theory of truth and true objects or whatever, then it becomes something along the lines of a Comenius language, where every well-formed formula is a truism, and it reflects all the truisms, so anything that's a model can be pulled out of that. And then it gets into whether those are negatory or affirmatory statements themselves. So there might be a usual idea that it's actually negatory first. It's like, what is truth? It's like, that's not true, that's not true, that's not true, that's not true. What is that to mean? It's like, well, it comes out about in a roundabout way that kind of static, that kind of the vacuous, that kind of the trivial is in that kind of universal. ends up being the real objects of the mathematical universe that are these objects of logic in the universe. For technical philosophy, at least one of them, it is like so. Then the affirmatory kind of follows from that. So that first there's true, and an iota of false, but only a prototype of what could be false. Then there's a negatory, and then there's affirmatory, and then they sort of make what become the airy of a sort, and the mathematical objects in structure and form. Because the idea that then you can take axiomously anything by what are these principles of objects of relation, there's basically posited the existence of identity, tautology, and negation, or the inverse, as was mentioned. That then for these properties, that there's diversity and variety to so follow that. And so for this constancy and consistency and completeness and then concreteness, is that the nous really kind of includes the phenomenon. The mental universe abstractly is the real universe. This is for a technical philosopher to arrive within without any further ado, without any further ontological commitment. God himself could have this theory. Respectfully, and not so much for fear of a deity, but just to respect other people who have very strong ontological commitments to any such matters of authority in their philosophy, is that it's truth. And so anything that's really the arbiter of truth would have the same kind of theory. And then that is the same thing as Plato's ideals and these kinds of forms. And then it's advised later, which was all built up as classical regular rulal, and all such things that arrived at both for inductive and deductive inference. And everything that became and is classical for the logical. Platonism. That then there's that Kant's as an example, and we can point to Spinoza and also Duns Scotus. One of my favorites is Duns Scotus for infinity. Infinity is real, he said. That these technical philosophers arrive at that these non-classical superstandard fundamental objects of like the Ding-an-Sich and the noumenon are all the things. All the things are in this manner, this way. And so without further ado, without further ontological commitment at all, there's never any further ontological commitment to a technical philosophy ever anyways. So in this manner, I feel like I've contented myself that at least now that I know there is a universe and it has its truths, then anything else is a matter of application and exercise. It's a science. It's statistics. It's abstract, and it's an art. It's the applied. It's anything that arises from my ontological commitment to any other metaphysical or physical models and their interpretations to any other metaphysical, physical models interpretation. Then there's for the making of how that makes for the very concrete connections directly to the objects of the mathematics that are primitive and elementary. These being the most necessary ones to establish all of the objects of mathematics. There's geometries, points and spaces. As long as the finish line is that you can end up with something equi-interpretable with Euclid's logic, then all that history has equipped geometry with is free. It's equipped. So it becomes very standard in what results that there are models of it that fall out of that are the standard. And similarly for a logic, logical objects from our technical philosophy, greatest minds. And then it's similar for other aspects like words instead, where words are both the numbers of members of a mathematical theory of formal languages and formal automata, and then also the descriptive, kind of like in the Kabbalah is an ancient mystical tradition of Judaism in the study of numerology and words, like the tetragrammaton and the gematria are the study of the letters of the names of the deity and the numbers and their symbolry. That's technical. It's just a matter of that. At the same time, it's connected to all kinds of mysticism, and there are many efforts that interpret it and are without connection to deeper, relevant, concrete things, but they connect to ideas and ideations and this kind of thing. That it's just an example, though, that since longest recorded history, the notion of answering the technically philosophical question, why is there not nothing, starts all the books that were ever printed, and so it ends up being part of this one too. So, and that keeps things simple. Again, the goal is to have, for all these talks, for all these readings, for all these books, for all these theories, they boil down to one word soup that's nutritious. And they boil down to one overall concept that is what I consider the best investment in an ontological commitment that can possibly be made, because it's always true, even if I don't know what it is. And then that also then figuring out how that connects, and the objects are not always intuitive in their properties, but they relate in their complements. You have to be totally it's a totally honest endeavor. It has to be that the conscientious logician can never ignore any alternative. It must fall out or trail out. And of course it need not be followed out what's false, but what it really is inconsequent true must be so. And then this helps also that whatever appears intractable or insoluble or not by any real thing to be so or true, but must have some way. It may have many ways. Those are the kinds of things that make for that. This is, from what I can figure out, is the least sort of ontological commitment of a theory. It's called a theory, axiomless theory, but a theory. It is that the results are that it is the most valuable in terms of the most fundamental. It's the theory of everything. And so, anyways, carrying on in this second course of differential analysis, is that differential analysis for all things in a continuum of space and as by quantities in the field norm or formalism, and how basically physics has as a model of all the objects of the physical universe, the concrete, that they do live on such a thing where time is the parameterization of these events in their ordering in according to the space where they exist. That so for Hegel, it was after Kant. And again, we're not talking about like Hobbes and Leviathan and that kind of stuff. All we're talking about is Kant and his technical components to a higher order technical philosophy with elements that are primary, and about the Ding-an-Sich and the noumenon, and that it fulfills a monadology for Leibniz. Okay, and then Hegel, and then Kant's other idea was being, and so this is being. It's not so much that being is like I am, therefore I am, or I am what I am, which is also a reflection in being. There's nothing wrong with that at all. But that then Hegel basically stands up for nothing. He's like, well, what about nihilism? So we can think of Hegel as kind of a weak echo of Kant, where Kant was like the poster boy of all our highest technical philosophy of the time, with the approbation of the orders of authority. And then there's Heidegger, and so we get to being, nothing, and time. Time is, in a sense, this third concept. And it represents change, and the geometry is motion. Change is constant, and the constant is change. And it helps reflect that a constant and a variable are the same thing. And at the end of the day, there's only one mathematical object, all the mathematical objects. And this very reflection on these kinds of things is then what makes for when it's possible to have explored enough of that and having a technical philosophy that's a fair dialectic, that's open, honest, and conscientious all throughout. It's a theory of truth and brings together all the necessary things to make it so possible that there's what comes in as the needful of all the desiderata and requirements of a theory for formalization for the constructivist and the intuitionist, and the science of the theory of mathematical objects and the objects of the realm of thought for object sense, objectivism, that this is the kind of utter foundation that one has to get into at all if you want a theory of everything at all. And in fact, then it results that there's no 2 cents, as it were, about it. That being an apocryphal expression that an opinion is worth 2 cents, and it's that is some value. That is some value. There are no 2 bones about it. There are no bones about it, or something like that. There are no it is alternation. It is alternatives. It is all the alternatives. There are none. There are no paradoxes. There are none. It is or isn't one, that it has none. So that, while kind of abstract, yet results that it's logically necessary and applied in the deductive analysis for a replete mathematics, and what would make for foundations and a proper candidate for a theory of everything, the theory that it's inclusive and there aren't any alternatives to it. So I have zero problems with an ontological commitment to it at all. It takes care of that for itself. Well, anyways, I hope this finds you well and good today. I hope the recording has been all right, and can kind of see, like, my vision is pretty poor. Where is that there? Looking around a bit. See whether that falls back later. Yeah, it's nice here. Hey, have a great day.